Space could be shaped like a giant donut, looping back on itself. That means distant directions can eventually meet again and wrap around. In plain terms, geometry tells how space bends on large scales. This changes how galaxies cluster and the angle sums of triangles. So the immediate idea, space can curve or loop, which matters. Stand on a vast plain of galaxies under a dark sky. Curvature means how straight lines bend across space. It decides whether parallel beams converge, diverge, or stay apart. Positive curvature focuses light like a sphere curving inward. Negative curvature spreads paths like a saddle stretching outward. Flat space keeps angles as Euclid predicted, no global bending. They show curvature is smaller than about 1% on cosmic scales. Quick picture, draw 3 straight lines across a balloon. That sets the stage for topology and large-scale patterns. Picture the infant universe boiling and shimmering like soup. Flatness asks whether space, overall, curves or stays Euclidean. This matters because it sets the universe's fate and geometry. If space were strongly curved, galaxies would distribute differently. Inflation stretches space enormously, ironing out any initial curvature. Think of stretching a crumpled map until it lies flat. Cosmic microwave background patterns pin down curvature with precision. They find curvature is tiny, within 1 part in 10,000. That flatness is not automatic, it's a cosmic clue. Some universes loop, so traveling far returns you home, surprisingly. Topology describes whether space connects to itself at large scales. It changes what we see across the sky and duplicates images. In a closed torus, a straight path loops indefinitely like a racetrack. Light can circle, producing repeated galaxy patterns, separated by angle. Detecting pattern repeats uses correlations in the microwave sky, mathematically. Searches looked for matched circles larger than about 1 degree across. So far, none convincingly, which sets minimum wrap scales near the observable horizon. Thus, topology asks if cosmic space loops, and we can test it. Zoom out until galaxies form a web of filaments and voids. This network, stretching hundreds of millions of light years, speaks geometry. Large-scale structure records how gravity and expansion have competed. Curvature slightly alters how density waves grow across cosmic time. Baryon acoustic oscillations act as a standard ruler, about 150 megaparsecs. We map galaxies to measure that scale and infer curvature. Surveys like Sloan and Dacey trace millions of galaxies precisely. Their data constrain curvature and the growth rate of structure, so the cosmic web stores geometry's fingerprint, readable by surveys. Small deviations inform dark energy models and cosmic history. Ancient microwave light arrives from a time when atoms formed. Its tiny hot and cold spots map sound waves frozen in place. Those angular patterns encode the universe's geometry and content. Curvature shifts the apparent size of these ripples on the sky. Gravitational lensing smears the patterns, which also reveals mass distribution. Planck and ACT measured these features very precisely across frequencies. Their results limit curvature to nearly 0 at high precision. Constraints imply any curvature is smaller than 1 part in 10,000. Thus, ancient light offers a precise geometric ruler. Visualize a distant quasar, its light bent around a galaxy. Gravitational lensing is light following curved spacetime paths. Lensing reveals mass and how space itself guides photons. A massive object warps geometry, so geodesics bend toward it. Light can produce multiple images, arcs, and faint rings around lenses. The specific image separations depend on distance, mass, and curvature. Einstein rings often span an arc-minute or smaller scales. Strong lens surveys find dozens of systems, useful for cosmology. Weak lensing measures subtle shape distortions over millions of galaxies. Combining lensing with the microwave background tightens curvature limits significantly. That cross-check reduces systematic errors and strengthens conclusions. The observable universe is bounded by a horizon of light. The horizon marks the farthest regions we can ever observe. Beyond it, topology or curvature could behave differently, unknown. Expansion stretches light, so distant signals never reach us again. Curvature affects comoving distances, changing the observable volume. Our horizon sits roughly 46 billion light-years away. If space wrapped at smaller scales, we'd see repeating structures. So horizons limit tests and hide possible global geometry features. Cosmology must therefore infer whole space properties indirectly, carefully. Remember the opening idea: space can loop or curve, and that really matters. We measured curvature using ancient light, galaxy maps, and lensing surveys across the sky. If you like this, subscribe for more curious cosmic deep dives explained simply today. Bottom line, geometry is strange, but it's measurable and deeply informative.